So, I will start with the introduction. In high-dimensional datasets, principal component analysis, known as PCA, is an effective statistical method for reducing dimensionality while maintaining the greatest amount of variation. In the context of cancer research, PCA may be quite useful in analyzing complex datasets with several properties such as clinical measurement or gene expression levels. Researchers may find trends, cut down on noise, and improve data visualization by converting the original variables into a new collection of uncorrelated variables. This research aims to use PCA on cancer datasets to discover underlying structures that might help with diagnosis and therapy approaches. Next is the data distribution. The study makes use of dataset that contains a variety of characteristics gathered from the cancer of patient. Firstly is clinical measurement. Next is the genetic information. Lastly is the demographic data. The dataset represents each patient as a single observation with a range of attributes that help understand their condition. For missing values and data consistency, the dataset is frequently pre-processed before doing the PCA. This ensures that the study will focus on data trends rather than the outliers or scale errors. Thank you.
For methodology, firstly, load the data set and remove the categorical variables. The supply function in the code is used to return the results in vectors, matrix, or a list. After that, standardize the data and compute the covariance matrix. The scale function is used in this code to standardize the data by centering and scaling. After that, the co function is to calculate the covariance between variables, while the eigen function decomposes the covariance matrix into its eigenvalues and eigenvectors. Following that, generate a script plot. The data frame in the code is to create the data frames. The ggplot function is used to create a variety of statistical graphs, including script plot. A script plot displays the eigenvalues in descending order. Next, calculate the principal components using the prcomp function in the code. After that, construct a 3D scatter plot to see the connection between the first three principal components. The plotly function is used to make the 3D scatter plot.
My name is Gaudian. So to check the normality of the principal components using the Shapiro wave test and QQ plot. Shapiro test function is used to perform the Shapiro wave test of the normality. So to build the QQ plots, the pair function is used to modify the graphical parameters of plots where the QQ norm function generates the QQ plot and the QQ line function is overlies a reference line. So next is the explanation of Mahalanobis. So to identify any outlier is using the Mahalanobis distance. The outlier are the observations that divided significantly from the center of the data distribution. So the Mahalanobis distance account for correlation between the variables and identify the multivariate outlier. The Mahalanobis function compute the Mahalanobis distance for each observation. So the Q chi function is you allow us to return the value of the chi-square quantile function. And the outlier are identified by comparing the distance to a chi-square threshold. So next is the R-code for the Mahalanobis distance. So we will use the 3D scatter plot to finding the outliers. Why we use the 3D scatter plot is to make it easier to interpret the data pattern and abnormality. So create a 3D scatter plot that overlies the original data points and the identified outliers. So from the codes, the PCA score data frame, which is a data frame that contains the principal component score, is plotted in blue, where the outlier data frame, which is a subset of the PCA score data frame, containing only the identified outliers, is plotted in red. So this is the R-code for finding the 3D scatter plot to find the outliers.
Okay, now let's see the result of script plot, QQ plot, and the 3D scatter plot. Okay, so first, the script plot and cumulative variance. Here is the script plot where it tells us how much variance is explained by each principal component. The elbow point is at PC3, meaning the first three components explain 88.7% of the total variance. After PC3, the additional components add very little information. So by keeping just these three components, we can reduce complexity but still retain most of the important data. Okay, next is the QQ plot. It checks if our data is normally distributed. The lines deviate from the diagonal, showing the data is a normal. The Shapiro wave test confirms this with very small p-values, where all the p-values is less than 0.05. So we can confidently say that we reject the null hypothesis, which is H null equal to the data is normally distributed. Thus, we can say that none of the three components following a normal distribution. Okay, last, this is a 3D scatter plot of the first three components. The blue points represent the main data cluster. These points are close to each other and the center of the plot, meaning they are relatively similar. The red points are the outliers where they scattered far from the main cluster, indicating unique or unusual observation. For example, this could represent errors or interesting cases that need further investigation. In conclusion, this analysis helps simplify the data while keeping its key features.
Hi, my name is Kelki Sheng, and before we proceed to the conclusion, let's talk about the justification on why do we choose to apply PCA on this dataset. So first, this dataset has high dimension with a total of 15 variables. And second, the variables in this dataset have relatively high correlation, making them suitable for PCA. And lastly, we want to transform the data into low dimension while capturing the maximum variability and reducing the redundancy of the dataset. So there are some implications on the medical field. First, dimensionality reduction, noise reduction, improved visualization, and also anomaly detection. In conclusion, PCA is successfully implemented in this dataset as it managed to reduce the dimension of the dataset from originally 15 variables into only 3 principal components while maintaining a total of 88.7% of total variances from the original dataset. That's all from us and thank you for your attention.